brains perform an estimated 10 trillion operations per second, requiring approximately 12 watts of energy, which is about the same as a light bulb. This energy primarily comes from a sugar called glucose, which is transported directly to neurons for their activation, and also to another type of brain cell called astrocytes. These astrocytes store glucose for later use by neurons, particularly during challenging cognitive tasks which demand attention and learning, and are processes which gradually deplete glucose levels. Together, this has led neuroscientists to theorize that this is why learning can feel so exhausting, because this mental fatigue signals that glucose levels are dropping too low and that you must conserve the rest. It is a long-held view within psychology that humans try to be as lazy as possible when it comes to cognitive processing. In other words, that we do our utmost best to avoid engaging in everyday tasks, which we experience as being mentally challenging, or which require long periods of sustained effort or attention. These kinds of tasks typically involve activities like studying, problem solving, or even challenging social situations. However, if we do end up having to engage in any of these kinds of activities, we typically experience a growing and unpleasant sensation of mental fatigue, rendering it very difficult to continue doing what we are doing for too long without any kind of break. Because of this mental fatigue, and because of our general preference for avoidance, cognitive processing is therefore considered to be aversive for the brain, in what is called the law of least mental effort. As a result of this, it is therefore thought by many neuroscientists that cognitive processing is a unique form of brain activity, in the sense that cognitive functions require a particularly large amount of brain energy to be performed. This is thought to be especially true for functions like attention, working memory, and self-control, and is in stark contrast to other brain functions like sensory processing or motor movement generation, which typically feel rather effortless for your brain to perform throughout your entire day. Therefore, this has led many neuroscientists to argue that cognitive processing seems to be particularly costly or computationally expensive for your brain, specifically in terms of your brain's metabolic resources, for which the underlying metabolic resource in question has long thought to be glucose. Glucose is the primary energy resource for neurons, and it is a nutrient that is obtained from the food that we consume. This glucose is then absorbed into your bloodstream, and this blood is then delivered up to your brain, particularly to areas which are becoming especially active, and are therefore in most need of the energy. However, whenever the levels of glucose in the blood drop to an abnormally low level, this low glucose state is called hypoglycemia. Hypoglycemia most famously occurs within diabetes, with cognitive functions typically being amongst the first functions to become diminished during a diabetic episode, whereas they usually retain the ability to perform simple motor acts. Furthermore, even in people without diabetes, conditions of low blood glucose that remains within a normal range are also associated with cognitive deficits, as well as mental fatigue. Therefore, even in people without diabetes, low blood glucose levels seems to be associated with an impairment in cognitive performance. However, what is surprising about this is that when these scientists have measured blood glucose levels during these cognitive tasks, the effects have been too small to explain the diminished performance that occurs. In other words, during high levels of cognitive activity, only small amounts of glucose from the blood is actually being used up by neurons, which suggests that this energy is being provided from somewhere else. Despite the fact that neurons are the most famous type of brain cell, astrocytes are in fact the most abundant type within your brain. Here they form a whopping 40% of your total brain size, meaning that they outnumber your neurons by about 5 times. Accordingly, your astrocytes are distributed throughout your grey and white matter, and your neural circuits are formed within these astrocytic networks. Here, blood therefore carries glucose not only to your neurons, but also to your astrocytes, whereby your astrocytes absorb the glucose from your blood in order to store this energy for neurons which may later need it, specifically in times of greater demand. In this way, glucose is stored by astrocytes in the form of glycogen, and amazingly, this storage of glycogen far exceeds the amount of glucose within your blood. Here, whenever neuronal activity increases, such as whenever you engage in some kind of challenging cognitive task, astrocytes then break this glycogen down into an energy substrate called lactate, which is then transferred to your neurons via an astrocyte neuron lactate shuttle. This lactate is then absorbed by your neurons and then used as energy to power the increasing demand that has been placed upon them, due to whatever intensive activity you are now engaging in. But how does the brain avoid running out of glycogen? So to briefly summarise, your brain requires a continuous supply of energy in order to function, with some functions obviously being far more important than others, functions like sensory processing or motor generation. And accordingly, whenever conditions of low blood glucose or hypoglycemia occur, your sensory and motor functions remain intact, whilst your cognitive functions show deterioration, and you experience mental fatigue. This seemingly serves to warn you that the glycogen that is stored in your astrocytes is getting too low. Therefore, in 2015, scientists named Thomas Christie and Paul Schrader proposed a model called the optimal control theory, in which they argue that our brains attempt to strategically conserve our glycogen energy by reducing our brain activity. Here they propose that our brains have a kind of energy budget, in which cognitive effort is actively avoided, especially when our brain energy has already become reduced. In this, it is argued that mental fatigue may therefore serve as a warning signal that your glycogen stores are at risk of becoming depleted if you continue to engage in whatever activity that you are currently engaged in, and informs you that you need to take a break. And to take this even further, not only does cognitive processing use up your valuable glucose and glycogen, but so does self-control, which may be why even simply attempting to make yourself do any work can often feel paralysing and almost impossible, trapping you instead in a period of procrastination, for which you need self-control and therefore energy to drag yourself out of. Therefore, procrastination may have evolved to stop you from using up any more of your valuable glycogen, at least until your glycogen levels have restored. And the main way that these glycogen levels become restored is through the process of sleep, with neuroscientists reporting that even just a 15-minute nap can restore our glycogen levels by around 70%. Here it is therefore thought that glycogen restoration is therefore one of the main reasons why our brains need to sleep, and has been proposed under the Bennington and Heller hypothesis. But you can find out more about that in future videos.